Hello, everyone. New day, new grind. Yes, yes. Yeah, I'm just gonna wait for people to arrive and start the presentation off at hopefully around 12:02 or something. New day, haven't gotten good at math yet. Yeah, same. And I'm presenting this. You should be worried. Just kidding. Just trying to get that pass. Yes, listen to the mod. HDs at this seminar. General Kenobi. Yeah, that's right. I said it. I'm one with the memes. It's I can understand. By the way, is the voice level good enough, or should it be higher? Should it be lower? Louder could be better. All right, I shall make it a little bit louder. How's this? Thank you, Ray. All right, nice. People seem to be joining now. All right, we're cheer just for you. I'll make it a little bit more loud. How's that? All right, it's all right. I'll just like enunciate a little bit more. Instead of just increasing the volume, I'll just like speak a little bit louder. Yes, the slides will be uploaded to UNSW mathsoc.unsw.edu.au after the presentation is done. So it should be available well before the exam. All right, it is 12:03 and 21 seconds. I think we should get started. As people join, they can probably figure out what's going on. So this is the second Math 1231 and 1241 revision seminar. This part is about calculus, is the calculus part of the course, right? So it'll be taught half by me and half by Gordon, right? So I'll be teaching the first half of this course. I'll be teaching functions of several variables, integration techniques, and half of ordinary differential equations, and Gordon will take over the rest. So Yeah, so in the middle, when I stop my side of things, we'll take like a maybe 5 to 10 minute break so that you can, just chill out, absorb all the content, maybe get a drink or something to eat, and then Gordon will take over after 5 minutes. All right. So are we ready to get started? Just hit that pog in the chat if you're ready to get started. All right, nice. Yeah, there's a little bit of a delay, so those messages took a little bit of time to come, but yeah, let's get started. All right, so first thing we're going to cover is functions of several variables. Okay, so as when we're dealing with functions of several variables, the first most important thing we have to deal with is partial differentiation. In two dimensions, we just had two variables, y and y was dependent on x, and so we could just differentiate with respect to uh, the x, right? But in this case, we have two variables. We have x and we have y. And so we have to make sure that we're differentiating only with respect to one variable at a time in order to make sure we can do it, because we can't really differentiate with respect to both variables at once. So in this case, we have an example. Let f of x, y, this is a multivariate function, be x squared plus xy plus y squared, right? And so when we're partially differentiating this with respect to x, we use this symbol. It's like a weird D kind of thing. It's a very curvy delta D looking thing. Or we can use this, which is just f, and then the subscript is the variable you're partial differentiating with. And so when we're partially differentiating, we treat all other variables as constants, right? So when we're differentiating with respect to x, this y, we can just treat it as like an a or a b or a c. It's just a constant, right? So when we're differentiating this with respect to x, the x squared just becomes 2x, right? The xy becomes y because y is just a constant multiplied by x, and the y squared is just a constant, so it just disappears completely. And the same thing when we're differentiating with respect to y. The x squared is a constant, the y squared becomes 2y, and the xy just becomes x. Okay, so people are saying it's lagging. Okay, let me see what I can do, if anything. Just a sec. All right, guys, I'm back. So I just moved a little bit closer to my router. If the problem is on my side, hopefully it should be a little bit better. Just tell me how we're going. If worst comes to worst, I'll just pursue through. I'll just like push through, and I guess just keep refreshing. Yeah, it's Twitch's problem. It's not my problem. Anyways, yeah, so let's keep going with our partial differentiation. And so the first kind of application of partial differentiation is when it comes to tangent planes to surfaces. All right, so a very well-known application for two-dimensional derivatives was that you could you could find the equation of a tangent line to a curve at a particular point, right? So in this case, we can just do the same thing, but with a tangent plane. And we can find a tangent plane to any surface we want if it's defined in 3 dimensions, right? So suppose that we have a surface over here which is defined with the relation z is equal to f of x and y, right? Then if we want to find a tangent plane to this curve, We know at the point P, x0, y0, z0, we know that it will have normal vector. This n is a normal vector. It'll have this normal vector. Now, this notation we covered on the last slide, it's just the partial derivative of f with respect to x, and the partial derivative of f with respect to y, and then a -1, and we evaluate this at P. So how does a normal help us get the equation of the plane itself? Well, we can use the point normal form of the equation of a plane to get this. So remember that from Math 1131 or 1141, that if you took the dot product of two perpendicular vectors, you'd end up with 0. And so say we take any point x on the plane and we take a p, which is the point on the plane that we're evaluating this normal at. So x minus p is obviously parallel to the plane, and the normal is obviously perpendicular to the plane, so the dot product of this must be 0, and that's what allows us to get our kind of equation going, right? So let's see an example of this. So let's say we have a function over here, a surface, defined with the relation z is equal to 4x cubed plus 3y to the fourth at the point 1, 1, 7. So x is equal to 1, y is equal to 1, and z is equal to 7. All right, so we first try to figure out our normal vector, which is just going to be the partial differential of f with respect to x, partial differential of f with respect to y, and then -1. So we differentiate we differentiate this part of our equation, which is just 4x cubed plus 3y to the fourth, with respect to x, and we get 12x squared. When we evaluate this at 1, we end up with 12. And same thing, when we differentiate this with respect to y, we get 12y cubed, which when evaluated at 1, yields 12. And so this is our normal vector. It's 12, 12, 1. All right, and then we do x minus p, which is just x minus 1 minus y minus 1, z minus 7. And then when we do the dot product, we get our equation, which is just 12x plus 12y minus z minus 17 is equal to 0, which is our equation of the plane. No way. Why is it so bad? Is it really this bad for everyone else? I'm so sorry, guys. I'm really not sure what's happening. Hmm. Alright, yes. I would follow the advice of not a pudding boy and reduce the quality to 360 from now. Best that we can do, I guess. Alright, let's keep going. Alright, so that was the case of a surface where we had this particular equation, right? We had z given in the form of an equation in x and y. What if we more generally have this plane? What if we have an equation g of three variables, x, y, and z is equal to 0, right? Like an implicit plane, like we had, say, the equation of a circle. That the equation of a circle in two dimensions would just be x squared plus y squared minus 1 is equal to 0. How would we find the tangent plane of that? So that's also a simple matter. It's just the normal vector at P on this surface G would be given by this kind of thing. So instead of the -1 over here, you replace it when you do by the partial differential of G with respect to Z. right? And so we can see that this is kind of just a special case of this more general thing, right? So in this case, we bring the z to the other side. It's just f of xy minus z is equal to 0, right? And so you can think of it as being a general case of this because and this looks a lot nicer anyways. So if you have a curve of the form g of xyz is equal to 0, then the normal vector would be this, this, and this evaluated at your point P that you're taking the tangent curve to. All right, so then we move on to this total differential approximation, right? So this is the form of the total differential approximation, right? We can see that is, say there we have a function f which is dependent on x and y, then any change in x is approximately given by this kind of thing. So this is the partial derivative of f with respect to x, which is kind of roughly the rate of change of f when x changes, and then this is the change in x. And then we add that to the rate at which f changes when y changes, and times that by the rate by the change in y to get approximately the change in f, right? And that this rationale is just given over here. So we can use the total differential approximation for some error estimation, right? The total differential approximation can be used to estimate the error of a variable that's dependent on other variables. So say we have f, which is just a variable, right? We treat f as a variable, a thing that we're observing, and we want to know how it changes. We want to know the error in our value of f given our errors in the value of x and y. So the error in the value of f is just the absolute value of delta f, right? And so we can use the total differential approximation and then use the triangle inequality to work out that it will just be less than, so we can get like an upper bound on the total error in f by this expression. So you multiply the absolute value of the partial derivative of f with respect to x times by the error in the value of x, and add that to the partial derivative of f with respect to y and multiply that by the error in y. All right, so in this case, we'll just have that, this is an upper bound, right? This is not a estimation. It is an estimation, but it's more so the highest that it can be, right? So this is the highest value of any potential error. All right, so let's keep going. So now let's talk about chain rules. It was kind of simple back in 2 dimensions when we had the one chain rule. It was pretty simple. It was just dy on dx is just dy on du times du on dx. But when we're dealing with more than one variable, we have more than one chain rule. So say we have a function f of xy, right? And the twist here is that not only are x and y variables themselves, they're also variables that are dependent on t, right? So we can use the total differential approximation to help us with this. So our total differential approximation just went like this, right? Say we divide that entire expression by delta t, and we get something like this. Now this looks very familiar, at least to me, just because those delta y on delta t and delta x on delta t and delta f on delta t are very reminiscent of derivatives. And so as we take delta t approaching 0, right, we'll get closer and closer to the instantaneous change in both f, x, and y, and so they'll approach their respective derivatives. Right, so delta f on delta t will approach df on dt, delta x on delta t will approach dx on dt, and delta y on delta t will approach dy on dt. So then we can simplify our entire expression to df on dt is equal to the partial derivative of f with respect to x times dx on dt plus the partial derivative of f with respect to y times dy on dt. And here I want to draw like some form of distinction, right? So when it was confusing for me initially, so I just want to clear that out in case it may be confusing for anyone else. When do you use a normal d, as in the derivative d, and when did you use the partial fancy d? So the distinction comes down to the fact that you're dealing with more than one variable. So f is dependent on both x and is dependent on y at the same time, right? It's a function of both x and y. In which case it'll be dependent, it'll be a partial derivative. However, if we go a little bit further, then both x and y are just dependent on t, right? So that's only one variable we're dealing with. In the end, f is just dependent on the variable t. And so in this case, it's just a normal derivative. There's no multivariate things to take into account. Right, and yet it is still quite confusing to deal with right here. So let's simplify our expression a little bit. All right. So here we have this cool looking thing. This is what's called a chain rule diagram, right? So we can use this chain rule diagram to kind of help us work through our partial derivatives when we're dealing with more than one variables. So here, this diagram kind of represents the same thing as before. So here we have a function f, which is dependent on x and y, changes with respect to x and y themselves change with respect to t. So we draw up a function chain rule diagram over here showing that f is related to x and y, shown by the outward arrows from f to x, and we also show that x and y are dependent on t, shown by the outward arrows from x through t. And these arrows, we annotate them with the respective differential operator. So when it comes to the relation between f and x, we do a partial f on partial x because it's a partial derivative, and when it comes to x to t, we do just dx on dt. And the same thing for y. And so this helps us in finding out our expression for our partial derivative, just because it works out in a way such that the expression for our partial derivatives, it's just if you trace the lines through to where you want to take the partial derivative of, and you add up all of the different routes, multiplying all the different lines there, then you end up with the expression. So let me explain that a little bit more. Over here, if we want to go from f to t, we can take one of two possible paths. We can go through x and then to t, and then we can go through y and then to t. So as we're going to x, we take partial f on partial x, and then we multiply that when we go from x to t by dx on dt. So the first part of it is just partial x on partial f, the partial derivative of f with respect to x, times the derivative of f with respect to t, right? And then we also have another path over here, which is just the path from f through to y, and then from y through to t. And so that gives us the partial derivative of f with respect to y times dy on dt. And so we have these two kind of things, and we just add them together to get our final expression for the for our derivative df on dt. Oh, nice. Hasse diagram. Yeah, it is kind of like a Hasse diagram, isn't it? So yeah, let's keep going. That was, as you can see over here, that was just slide number 1. So we have another one. So let's take another hypothetical scenario. Say we have f with respect, say we have a function f which is dependent on x and y, but x and y themselves are also dependent on s and t, right? Well, x is equal to x of s and t, and y is equal to y of s and t. So then we draw our chain rule diagram over here, and we get this, right? So how does this work? So previously we had f going to x and y, and then them both converging at kind of t. But here we have two variables that they're both dependent on. So we have a total of 4 possible paths. We have f that goes through to x and then to s, f that goes through y and then to s, f that goes to x and then to t, f that goes to y and then to t, right? And over here we have two different partial derivatives. So we have two variables that we're both dependent on. We have s and we have t, right? So we can take the partial derivative with respect to t or the partial derivative with respect to s. So if we're taking the partial derivative with respect to t, we need to, again, just find all the paths that go through t. So you can have one path that goes through x, from f to x to t, and one path that goes from f to y to t, and so we can add up both of them over here, and we have this. So the partial derivative of f with respect to x times the partial derivative of f with respect to t plus the partial derivative of f with respect to y times the partial derivative of y with respect to t. And that's the same thing that applies over here as well. Instead of the t, we just have an s because it's kind of the same thing. All right, let's keep going. Chain rules 3. This one's simple. Say we have a univariate function u, right? Only dependent on one variable, but then u itself is dependent on x and y. Again, drawing our chain rule diagram, we get two partial derivatives. If we want to go through x, we have to go through u. So this is just a df on du, right? It's not a fancy d just because it's only one variable that we're dealing with over here. But over here, it's a partial u on partial x or a partial u on partial y just because we're dealing with more than one. So we go from f to u to x, and we get d partial f on partial x is equal to df on du times partial u on partial x. And then the same thing over here for our y. All right, and then we deal with functions of 3 or more variables. I would just suggest that try your best to ignore this while I take you through the explanation. So we have a situation over here. Let f be a trivariate function. It's dependent on both x, y, and z. So f of x, y, and z. And now x, y, and z themselves are dependent on both s and t, right? So they're also bivariate functions. But s and t themselves are also dependent on u. So here we have this massive chain rule diagram. We get f, which is dependent on x, y, and z, x, y, and z, which are dependent on s and t, and finally we have s and t, which are both dependent on u. So say we want to work out df on du. Well, I can tell you right now that there's a possible total of 6 paths you have to go through. So you can choose one of where you want to go, right? You can reach u by going from f to x to s to u, from f to x to t to u, from f to y to s to u, from f to y to t to u, from f to z to s to u, from f to y to t to u, right? And here is our final expression. So this is the accurate chain rule kind of expression for when we're dealing with functions of 3 or more variables, right? You just have to continually trace the path through. It's buffering again? Great. I am not sure what's happening. Just kind of, I guess, try to read the slides. Sorry. All right, well, in any case, that does conclude our functions of several variable topic, and then we can go to integration techniques. So, with integration techniques, we're dealing mostly with trigonometric stuff, but there's also a bunch of other stuff that we can also look at. So, here we have some trigonometric integrals. We have 3 kind of main types of trigonometric integrals. The first type of which is the integral of this form, right? Sine to the m times x and cos to the n times x times dx, right? We can kind of simplify these into 2 main cases. Well, 3, but we'll get to the third one later. So we have sine to the mx times cos to the nx. If n is odd, right? It doesn't matter what m is. If n is odd, then you have to make these substitutions. Right? You take u as sine x, you take du as cosine x dx, and then this n separates into n minus 1 and cosine x, and then the cosine x dx just becomes a du, so this becomes an even number, and then with the even number you can split it into half and then use this to solve for it in terms of u, which is our sine x. Right? If that doesn't work out, we have another one. If m is odd, right, then we have u is equal to cosine x, du is equal to minus sine dx, and sine squared x is equal to 1 minus cosine squared x, which is to be used if m is odd but n is even. Right, so here we have a little example of that kind of thing in action. So here we have a case where n is odd, right? We have cosine to the 5th x. So we use these substitutions, right? So we separate it out into this kind of thing, where it's sine squared x times cosine to the 4th x times cosine x dx, right? And then this just becomes this. So how does it become that? Sine squared x just gets replaced with u squared. Cosine to the 4th x just becomes cosine squared x squared. And cosine squared x is just 1 minus sine squared x, which is 1 minus u squared. So it becomes 1 minus u squared squared, which is just cosine to the 4th. Right, and then this just becomes a polynomial integration. You can just integrate it using the power rule. And you get u cubed on 3 minus 2u to the 5th on 5 plus u to the 7th on 7 plus c. But we replace the u's with their actual value. So we made the substitution u is equal to sine x, and so we replace all the u's with sine x, and so we get sine cubed x on 3 minus 2 times sine to the 5th x on 5 plus sine to the 7th x on 7 plus c. Right, and you may be noticing that there is a third case, right, that I'm actually forgetting here. And that's what if both of them are even? In which case, I suggest you pray, because that is almost impossible to solve. All right, then we get to trigonometric integrals. So say we have an integral of the form either sine to the mx times cosine nx, or something like cosine mx times cosine nx, or sine mx times sine nx. Then you can use one of these kind of substitutions. So these just rely on the the compound angle formula for cosine and sine, and what happens if you add the plus and minus signs together. So when it comes to sine mx times cosine nx, then it becomes quite simple. It's just half of sine m plus n times x plus sine m minus n times x. With cosine and sine, it's a little bit more nuanced, right? Because with cosine mx and cosine nx, you're dealing with cos, right? So this is pretty simple. This is just m plus n times x plus m minus n times x. When it comes to the same thing for sine, you just flip all the signs, right? So here we have a plus, here we have a plus, and here we have a minus. Well, in the sine case, if instead of cosine mx times cos nx, we have sine mx times sine nx, and you flip it so that it becomes cosine m minus n times x minus cosine m plus n times x. In these two cases, you should always try to pick m as the bigger number between the two. If it's the same, I guess it doesn't really matter. But if it's the same, then it's just sine squared. But if it's different, then always pick the bigger number out of the two to be m, because m minus n just makes things a whole lot simpler when it's positive. Right. Then we have some more trigonometric integrals, right? So when it comes to the trigonometric integrals, the third type, it's powers of tan and sec. So there's no kind of set cases on how to do this. It's always a little bit of figuring out every time. But these important identities can kind of assist you along the way. So our first important identity is tan squared x plus 1 is sec squared x. Right? This is very important. And also, the derivative of tan x is sec squared x, and the derivative of sec x is just sec x tan x, right? So here you see that they're all like kind of interrelated, and so it makes for a wide variety of possibilities when it comes to integrating powers of sec and tan. So say we're integrating tan squared x, right? So by this identity over here, I know that tan squared x is just sec squared x minus 1. Right? And then by this identity over here, I know that sec squared x is the derivative of tan squared x, which means the integral of sec squared x has to be tan x. The integral of minus 1 is just minus x, and we add a plus c in there for posterity. Right, let's look at this other example over here. So when it comes to the integral of sec to the fourth x times tan x, right, initially it may not appear to, you can do this in one of two ways now that I think about it, actually. You can use this substitution over here, but I think I noticed that this substitution would be a whole lot more convenient. So say you take u as sec x, then du is sec x tan x dx. And that's what I've done over here, right? I've separated the sec to the fourth x times tan x into sec cubed x times sec x tan x dx. This whole thing just becomes du. This thing becomes u cubed. This just becomes u to the fourth on 4 plus c because of normal polynomial integration rules. We replace the u with sec, and we get sec to the fourth x on 4 plus c, right? But you can also take the substitution u is equal to tan x, right? And then du just becomes sec squared x dx, right? And you have the sec squared x, which is just tan squared x plus 1. So you can also kind of approach it in that way, if that makes sense. All right, let's keep going. The next on our agenda is reduction formulae. So reduction formulae, they're kind of hard to explain. It's best to just do it with an example. So continuing with our tan and sec theme over here, we have an in expression, right? This n is a variable. It can change. It can be I1, it can be I2, it can be I5, whatever. So we take in and we set it to be the integral, the definite integral from 0 to pi on 4 of tan to the n x dx, right? So when this is I0, this is just 1. When it's I2, it's tan squared x dx. When it's I4, it's tan to the fourth x dx, and etc., etc. So we have to find a reduction formulae in terms of in minus 2. What this means is we need to reduce a problem, the problem we have in in to in minus 2. And this is really helpful because it allows us to kind of simplify our working from a, when we're dealing with something like I5, for instance, we can simplify it to I3 and then I1, and then when we have I1, which is just the integral of tan x, then it becomes quite simple to just integrate it. So in order to do this reduction formulae, we use our previously discussed identities. So we have the integral of tan x is just the integral of tan n minus 2 to the n minus 2x times tan squared x, right? Tan squared x is just sec squared x minus 1. And so we split this integral into two halves. We split it into this half, which is 0 to pi on 4 of tan to the n minus 2x times sec squared x dx, minus the integral from 0 to pi on 4 of tan n minus 2x dx. And notice what's cool about this is that it's n minus 2. It's the same thing as this, except we've reduced it to n minus 2. This is just I of n minus 2. And this, on the other hand, is something we can solve easily using our u substitution, which is just u is equal to tan x. And then sec squared x dx just becomes du, right? And then this becomes u to the n minus 2, which when we integrate just becomes u to the n minus 1 times n minus 1 from 1 to 0. So since we're making the substitution u is equal to tan x, we have to change the bounds of integration, always remember. So so tan of 0 is just 0, so our lower bound remains 0, but tan of pi on 4 is 1. So the upper bound becomes 1. And so we arrive at this expression for our thingo. Right. So, yeah, so speaking of I5, right, use the reduction formula we have obtained on the previous slide to work out the value of this. Okay, cool. So, we have the integral from 0 to pi on 4 of 10 to the 5th x dx, okay? And now this is just I5, okay? When we look at this, this is just I5, and we have a nifty little formula for reducing I5 into little pieces. So I5 just becomes 1/4 minus I3. I3 just becomes 1/2 minus I1. Since it's in the brackets, it becomes plus I1. So we have this expression, which is a whole lot more simple than this expression that we started with. So minus 1/4 plus 0 to pi on 4 of tan x dx. A little bit of a spoiler, it's just ln of sec x, right? From pi on 4 to 0. And so you get that this is ln of root 2 minus 0 minus 1/4, and so you get this. That is actually, I think that's incorrect. That shouldn't be that. That should not be root 2. It should be the natural log of root 2. It should be half of ln 2. See, this is why corrections are important. All right, I'll correct this on the slide that we publish. I think it's in the next week. No, it should be in this week in a few days, I think. Yeah, I'll correct this one. Yeah, so this is just a half ln 2 minus 1/4. And that's how you use reduction formulae. All right, so our final part of integration techniques, we have two equivalent things. We have trigonometric substitutions and hyperbolic substitutions. So these just arise when you see equations of the when you see expressions of the form this expression in your integral. So anytime you see a square root which involves a, which is where a is any constant, right? So a squared minus x squared, then you can substitute x is equal to a sine theta and dx is equal to a cosine theta d theta. Why is this important? Because a squared minus a squared sine theta is just a squared cosine squared theta because of our handy Pythagorean identity of 1 minus sine squared theta is equal to cos squared theta. And so you can, bounce out of that root. Same thing applies when you see something like a squared plus x squared. So x is equal to a times tan theta, and dx is equal to a times sec squared theta. This is also helpful because of the identity we previously learned, where 1 plus tan squared theta is just sec squared theta. And finally, our last kind of thing is just the root of x squared minus a squared, which is where we use this because, of the identity we just mentioned, and we substitute this. Right? And, these are fine, but they're kind of not very cool to deal with. No, they're fine, actually. We also have an alternate form for both of these. So we have our hyperbolic substitutions. So these, if you notice, they're exactly the same kind of thing. It's just that you substitute something else. So over here, we substitute a is equal to tan h theta, and dh is equal to sec h theta d theta, right? In this case, when we have a squared plus x squared, we substitute x is equal to sine h theta and dx is equal to a cos theta d theta. And over here, when we have x squared minus a squared, we substitute x is equal to a cos theta, dx is equal to a sine h theta d theta. Because these are our hyperbolic trig identities. They're different to our normal trig identities, which is kind of confusing at first. So instead of cosine squared x plus sine squared x is equal to 1, we have cos h squared minus sine h squared x is equal to 1. And similarly, the identity we just learned about the tan and the sec, well, forget about that because we have a different identity for tan h and sec h. 1 minus tan h squared is equal to sec h squared. All right, so these are two equivalent kind of identities. You can just use one depending on your preference. If you want to stick to normal trig, that's absolutely fine. If you want to go do the hyperbolic trig because you're fancy, go ahead. So, unless the question mandates it, in which case it does. So, say we have this integral, and we're given that we have to solve it through the substitution x is equal to u tan h theta. All right. So then we substitute u is equal to 2 tan h theta, right? And by our previous thing, we get that it is dx is equal to a sec h theta d theta, right? So we replace this dx with 2 sec h theta d theta. And this part, all right, so 1 minus tan h squared x is equal to sec h squared x. And so 4 minus 4 tan h squared x will be 4 sec h squared x, which when we take the square root of that just becomes 2 sec h theta. So we cross over both the sides and we just get d theta. And so we just get theta plus c, in which case we have to work out what theta is in relation to x. So we divide x by 2, and then we take the tan h inverse of that, and that's what we get for our value of theta. And so the solution to this would just be tan h, the inverse tan h theta of x minus x divided by 2. Let me say that again. Okay, so the solution to this problem is the inverse tan h of x on 2 plus c. Cool beans. All right, and now we move on to our final kind of thing of the day. Just gonna hover at this example for a little bit, just because it's quite a weird example with our new kind of hyperbolic trig identities. But yeah. So I personally pronounce them like sine h, and sometimes with cosine h, I say cos h sometimes, or cosh. I have no idea. All right. I was just responding to Abdullah there in the chat. So let's move on to our ordinary differential equations. Right. Equation is just an equation which describes a relationship between a particular variable and its first and second and really nth derivatives, right? So here we have three examples. Sorry, I can't count anymore. Here we have an example. For those of you that did, I'm not sure where this was in, but a lot of you would recognize this as being exponential growth and decay. So if the rate of change of a population is dependent on the population itself, then that's called exponential growth or decay, depending on if this is a plus or a minus sign. For many of you others would recognize this one over here, right? This is the simple harmonic motion equation, Hooke's law for springs, where the acceleration of a particular variable is dependent on its displacement away from the equilibrium. Again, another differential equation. And over here we have Newton's law of cooling, where the rate of change of a temperature depends on its difference from the room temperature, right? So if it's below room temperature, it will kind of try to rise up to room temperature. If it's more than room temperature, it will kind of try to go down to room temperature. All right. So our first type of ordinary differential equations are initial value problems. An initial value problem is an nth order ordinary differential equation. So like an nth order ordinary differential equation is just one that's, the nth derivative and all the other derivatives as well, optionally. But one that has a set of values for the variable itself as well as all the derivatives until the n minus 1th derivative. So say we take this example over here, right? I'm not going to go through this example right now just because Gordon will cover that in his half with second order ordinary differential equations. But say you have this example and that you're given that when t is equal to 0, then y is 17 and y prime is negative 1. That's a perfect initial value problem. What I will solve is this simple thing. So say you're given that the second derivative of y with respect to x is dependent on x cubed. Given that y prime of 2 is equal to 5 and that y of 0 is equal to 1, we have to solve this equation. All right, fine, let's do that. So we integrate both sides of this, right? The integral of the second derivative of y with respect to x is just the first derivative of y with respect to x. And this just becomes x to the 4th over 4 plus c. But we have a handy little simplification trick over here. So since y prime of 2 is equal to 5, we just substitute in 2 where x is and 5 where y is, where y prime is. Okay, so we get 2 to the 4th on 4 plus c is equal to 5. 2 to the 4th is 16. 16 divided by 4 is 4. Plus c is equal to 5, so c is 1. And so we get our definitive value for y prime. Y prime is just x to the 4th on 4 plus 1. So we keep this going. We integrate it again. And we get, what do we get? We get this little thing, right? So we integrate x to the 4th on 4, we get x to the 5th on 20. We integrate x, we get x squared plus 1 plus 2 and plus c. So now since we know that y of 0 is 1, we can work out the value of c to be 1 as well. And so since c is 1, our final equation just ends up being this. All right, nice. So now we come to separable ordinary differential equations. So a separable ordinary differential equation is one where both of the variables that are involved in the ordinary differential equation, y and x, can be separated into two halves of the equation with either half on either side. Right, so when we're dealing with the dy, we can have all the y's on one side, and when we're dealing with the dx, we can have all the x's on one side, which just makes it simpler to kind of integrate it at the same time and then work it out later. So this is an example of a separable ordinary differential equation. So say we just divide the whole thing by y squared and then we multiply dx on both sides, we can separate this out pretty easily. This is a self-contained integral, and so is this. This is also a self-contained integral. So just as an example, let's kind of do this one, where we have dy on dx is equal to y times x to the 4th. So we divide both sides by y and we multiply both sides by dx. And we get that the integral of dy on y is equal to the integral of x to the 4th dx. Right? This just becomes ln y, this just becomes x to the y on 5. We exponentiate both sides, we get that y is equal to e raised to x to the 5th on 5 plus c. Right? And a useful trick that you can do over here is that since it's an exponential operator, e to the a plus b is just e to the a times e to the b. Right, so e to the c, we can just set it as this variable a and forget about it. So we have it's a times e raised to x to the 5th on 5. And this value of a we can only ascertain if we're given the initial value. Something like when x is 0, y is 1, in which case c would be 0. C would be 0, a would be 1. All right, now we come to first order linear ordinary differential equations. So I kind of spoiled this one for you, but this is what a first order linear differential equation looks like. It's just dy on dx plus f of x times y is equal to g of x, where f and g are both functions in x. So this is like a first order linear equation, ordinary differential equation. We have 2 times dy on dx plus 4x cubed times y plus is equal to 3x. So our f of x in this case would be 4x cubed, our g of x in this case would be 3x. Right, so how do we solve first order linear ordinary differential equations? The trick is this part, which is kind of trippy, but it's cool when you realize what's going on. So we write the ODE in the above form, and this includes there being no coefficient of dy on dx. So in this case, we had a coefficient over here, in which case, to convert it into this form, we'd have to divide the entire equation by 2. So we write the ordinary differential equation in this form, and then we calculate our integrating factor, which is just h of x, which is e raised to the integral of f of x dx when we ignore the constant. This makes sense in a bit. So when we calculate h of x and then we multiply our ordinary differential equation by h of x, we get this. And then because of the product rule, we can say that this is equivalent to this expression. And that becomes really, really kind of simple to integrate and find out the final expression for. So we're solving first order linear ordinary differential equations. Let's solve this monstrosity over here. So we have x minus 1 cubed times dy on dx plus 4 times x minus 1 cubed times y is equal to x plus 1. And we're given an initial value over here, so we can work out an exact solution. So firstly, we have to express our differential equation in the proper form, which involves dividing the entire thing, this entire expression, by x minus 1 cubed. And so we get this kind of thing. Looks cleaner, is cleaner, debatable. So our f of x in this case is 4 times x minus 1 to the negative 1. So 4 divided by x minus 1, basically. So we have the integrating factor, which is just e raised to the integral of 4x minus 1 to the minus 1, which is just x minus 1 to the fourth, as it turns out, because e raised to 4 times the natural log of x minus 1 is e to the fourth times, it's e to the ln x minus 1, which is just x minus 1, because that's how exponentiation works, raised to the fourth power, which is just x minus 1 to the fourth power. So we multiply the entire expression by the integrating factor. And now you can see kind of where this is going, because our entire expression simplifies to this. So since it simplifies to this, we can kind of integrate both sides with respect to x. And since this is, a differential anyways, we just integrate it and we get rid of both of them because they cancel each other out. And we get that 4y times x minus 1 to the fourth is x cubed on 3 minus x plus c. So in order to get rid of the c, we can substitute our initial value in there. Y of 0 is equal to 2. So substitute 0 where x is 1, and then substitute 0 in the place of x and 2 in the place of y, and we get that 4 times 2 times negative 1 to the fourth is 8, which is equal to c. So since c is equal to 8, we can finally work out our actual full expression for y, which is this. All right, just a second. All right, let's continue. And for my part, the final type of ordinary differential equation we'll be looking at is exact ordinary differential equations. So these are kind of weird. These are really, really wacky. They're of the form this, right? So we have a multivariate function of f and a multivariate function of g divided by the derivative of y with respect to x is equal to 0. And not only do we have that, if it so works out that the partial derivative of f with respect to y and the partial derivative of g with respect to x is equal to they're equal to each other, then we have a very, very simple and elegant solution for our ordinary differential equation, which is just h of x and y is equal to c, where the partial derivative of h with respect to x is f, and the partial derivative of h with respect to y is g. And c is just a constant that we can work out using our initial values. So yeah, this is kind of crazy to look at, to understand, but it's not really too insane when we kind of go through an example. So we just have to show that this ordinary differential equation is exact, and then we have to find its solution. So we multiply both sides by 2y plus x minus 1, and then we bring that to the other side, and we get this. Now, is this an exact ordinary differential equation? What's the criteria? So the criteria is that when we differentiate f with respect to y, and we differentiate g with respect to x, it has to be the same thing. So we differentiate this with respect to y, and we get 1. We differentiate this with respect to x, and we also get 1. And so it is an exact ordinary differential equation. So it is an exact ordinary differential equation. All we need to do is work out our value of h of x and y. So we can work this out through a kind of method which is kind of hacky, but it works. So we are given that this has to be fulfilled by our h, right? dh on dx has to be 2x plus y plus 1, and dh on dy has to be g, which is 2y plus x plus 1. Okay, so we differentiate this with respect, we integrate, sorry, this expression for f with respect to x to kind of get our value of h. And notice this constant over here is it's with respect to y. And why is that? Why is that? Anyways, this constant is with respect to y just because of the fact that any variables in y are ignored when we're partial differentiating with respect to x, and so we kind of add them back in the form of this constant function. Right, and so we do the same thing for the other side. We do the same thing when we're integrating g with respect to y, and we get this function where we have the constant as a function of x. And so we kind of have to compare our two forms, right? The xy is common to both. This is xy plus x squared plus x. This is xy plus y squared plus y, right? So when we compare both of them, we can obviously see that c1 of y is just y squared plus y, and c2 of x is just x squared plus x. And so this becomes our h of xy. And so the solution to this exact ordinary differential equation is x squared plus xy plus y squared plus x plus y is equal to c. And so you may be wondering, why isn't there a c over here? Just because there's a c over here, right? And it's customary to kind of ignore it when you're solving for it. And we can probably work out c, but that's subject to initial conditions. So say we were given that y of 0 is 0, then we can work out the c0 of y of 0 is 1. Then we can work out that c is 2, etc., etc. But yeah, that's kind of a method to solve exact ODEs. They're definitely the weirdest kind of ordinary differential equations, but you know, there is a method to the madness. Right, so I am over. My time is up, and it is Gordon's time now. But just to give you guys a little bit of time to relax, kind of get some snacks, absorb all the content that we've covered. We've covered half of the entire calculus part in just over an hour. So I'm gonna stop streaming now, and then we're gonna wait 5 to 10 minutes ish, before Gordon starts with second order ordinary differential equations, and then he takes you through Taylor series and the applications of integration. All right, bye guys.